So let's take a look here at mapping notes number 3. First of all, we've looked at maps like this. We understand these are physical maps and they show us what the land looks like in a particular area, where it's high, where it's low. But there are some limitations here. One of the disadvantages of using a map like this is that it doesn't give us a very exact measurement. It only gives us a rough idea of where the mountains are. It doesn't tell us anything about an actual measurement. All it gives us is a range. So to summarize this, the disadvantage of a typical physical map is that it's not very exact. It only gives us a range of elevations. Now, we're going to start talking about topographic maps. And to understand what they are and what they tell us, we need to understand what this word topography means. All that is a study of the Earth's surface shape. Where is it high? Where is it low? Is it flat? Is it steep? Are there mountains or are there flat plains? A topographic map is a map that details the physical shape of the Earth's surface. And primarily here we're talking about elevation, or how high something is above sea level compared to some other place. So a topographic map is different from the other physical maps that we looked at, in that a topographic map actually gives us numbers. It doesn't give us just merely a range. It gives us actual numbers that we can read about elevation. So that's how topographic maps are different than those colored physical maps. They give us actual measurements, not just trends. Now those lines that we see on these topographic maps, we've been doing these, and we understand that each line shows us a change in elevation, where you go up a certain amount. But we haven't given these things a name. These are called contour lines. These are lines that we draw on these topographic maps that connect points of equal elevation. So we know that every place along that line has an elevation of 5, 10, 15, 20, or 25. Now, we don't draw a line for every single elevation, because the map would just get too crowded and it would get too hard to read. It's like reading those millimeter lines on a ruler. When they're so close together and there's so many of them, it gets to the point where the map would not be very usable. So instead, we spread the lines out and we only draw a number on about every fifth line. We don't draw numbers on every line because the map would get too crowded and it would get too hard to read. So typically we draw a line every fifth line. These extra dark lines that have numbers with them are called index contours. Those are the ones that we actually measure from, and they're typically every fifth line. The question now becomes, if we don't have a number for each line, how do we figure out what each line represents? Well, what we're referring to there is called the contour interval. It's kind of like a scale. It tells us how much the elevation changes between each line. That's what the contour interval is. It's a scale that tells us what the elevation is changing between each line. And it can be different for different maps. The question is, how do we figure out what that contour interval is? Because if we don't know what each line represents, it makes the map unusable. We have to know what those lines mean, or how much are you going up each line. And there's basically 2 steps that you take. 1, you look at the index contours, those extra dark ones that have numbers on them, and you figure out, well, how much have you gone up between those index lines? And you can see in this case here, we've gone up from 200 to 300. But we don't know what those lines are in the middle. To figure out what each line represents, you have to take the change between the numbers, which in this case is 100, because we go from 200 to 300, and you divide by how many steps you have gone up in elevation. Well, look at this map at the right. Starting at 200, how many times do you go up to get to 300? If you follow along with me, we start at 200, we go to that line that has B on it. That's one step. We go to the next line. It's 2 steps. The next line, 3, 4, and by the time we get to that letter A on the 300 line, we've made 5 steps going up. So we've gone up 100 and we divided it into 5 steps. So our contour interval for this map would be 20. Each line represents going up 20. And I know that because 300 minus 200 is 100. So there's a difference of 100 between those index contours. But we took 5 steps to cover or go up 100. So 100 divided by 5 means each step that I went up is 20. Now this isn't always going to be the same for every map. Just like different maps can have different linear scales, like 1 centimeter can equal a mile, or 1 centimeter can equal 20 miles, or 100 miles, or 1,000 miles. These contour intervals can be different depending upon the land that you are showing. If you're in a place like Colorado with a lot of really high mountains that are really steep, a contour interval of 20 would mean you'd have a ton of lines on the map. And it would get too many lines on the map and you wouldn't be able to read anything. So in a place like Colorado, you might want to have an interval of 1 line equals 100 feet or 1,000 feet. But someplace like Florida, where the land is really flat and there really isn't much change in elevation, we might want an interval of 20 or even 10. So these intervals can change depending upon the map. So you have to be able to look at the map and figure out what the interval is, otherwise you can't make the measurements. Let's talk about gradient. Now gradient is a fancy sounding term, but let's look at what it shows us. If you look at these 3 points here, the 3 red stars, what do they all have in common? Well, they're all at 1,000 feet up. They have the same elevation. But is there a difference in how you get to 1,000 feet? Look at these paths. Look at 1 and 2. If you walked up 1 or 2 to get to that 1,000 feet, it's about the same either way. But route number 3, the steepness of that land is different depending upon where you are. The first part of it has a certain steepness, then it goes kind of flat, and then it gets steep again. But it is less, overall, it is less steep than if you walked up route number 4. Finally, 5 and 6. 5's an easy walk. It's not very steep at all. 6 is almost impossibly steep. It's vertical. It's like a cliff. So they all go to 1,000 feet, but they all get there differently. That's what gradient is. That's basically how much does the elevation or the height change to compare to how far you go forward. So in a nutshell, the most basic way to describe what gradient is steepness. How steep is the land? When the land is flat, it is said to have a shallow grade. That's what it means to be flat. It's not going up very much for every step you go forward. On the other hand, someplace that's hilly is said to have a steep grade. You go up a lot for every step that you go forward. So you'll hear these 2 terms. A shallow grade means flat. A steep grade means hilly. You'll see these signs on the road a lot. 6% grade, 7% grade. And it tells trucks to use a lower gear because trucks can't handle that kind of steepness and they'll get going too fast and then won't be able to stop. Here is the steepest street in San Francisco. San Francisco is notoriously steep and hilly, and you can see how steep the land is. This is a very steep grade. I took another picture of this same house, the same street, and I turned it so that the street is horizontal to give you a good sense of how steep this land really is. That would be like if the street were flat, that's what the house would look like. So this is a very, very steep grade. Some of the steepest streets in our country. Now, the world's steepest street is in Dunedin, New Zealand. It has a 35% grade. Here's a picture of one of the houses on that street if you turn the street sideways. And this gives you a good sense of how steep this land really is. The steepest street in the United States has a little section of it. It's about 37% grade. And not the whole street, but there's a part in the middle where it's 37%. In the wintertime, they actually have to close this street because it's so steep. When it gets snow and ice on it, you can't even drive up. They do host a really challenging bike race on this every year, and the bikers have to do loops on this street and have to go up that 37% grade hill, and it's extremely challenging. A railway like Lookout Mountain, if you've ever been there, has a 72.9, almost 73% grade. If you've ever been here and ridden the incline railway, you know that's a really steep grade. The steepest mode of transportation I could find in the United States is Royal Gorge. They have an incline railway. It's almost an elevator. It goes up at a 45-degree angle, which is 100% grade. That means for every meter you go forward, you also go up a meter. Now, how do we calculate grade? Grade is calculated by dividing the height that you go up by how far you go forward. Now, sometimes we can't have such a steep grade. We want to change the gradient of the land. We want to make it not so steep. For example, big trucks can't go up a really steep road. For most roads, typically for highways, about the maximum you can have is about 8%. Anything higher than an 8% grade, and it's unsafe for vehicles to travel on, especially big trucks. Now, if it's a neighborhood road, your driveway, you can have a steeper grade because you're not going as fast. So what do you do if the hill is too steep, but you need to make a road to get to the top? Well, remember what gradient is. It's the height going up and the distance going forward. So you got to change one or the other. You can either make the distance going forward bigger, or you can make the height going up less. Either one of those will change the steepness of your road or your path. Here is Lombard Street in San Francisco. This is what they call the world's crookedest street. This hill was so steep that horses and wagons couldn't go up and down this very easily. So they needed to get up and down this hill, but they couldn't have it be so steep. So what they did was they made the street longer. Instead of going straight up the hill, they make it curvy, and that makes the distance of the street longer. And if you increase the distance going forward, you're going to make the grade less. This is why mountain roads tend to be so windy. They need to make the roads longer so the grade isn't as steep. It's tough to make a hill shorter. You can't cut off the top of the hill, so you make the streets longer. Something like this. There's no way that road could go straight up that mountain. It would be too steep. Even a regular car wouldn't be able to handle that trip. So they make the road go back and forth. You go to the same height, but you take longer to get there, which makes the grade less. Same is true for hiking trails. If you've ever done a hiking trail and you do what's called a switchback, where you go up the mountain, but you don't go up in a straight line. Because if you look at this picture here, there's no way you could walk straight up this. You have to wind back and forth, which makes the path going forward longer, which will decrease the gradient. Same concept with things like this in a parking garage. It's a ramp. You need to get to the top of the parking garage. It's too steep to come straight down, so they make it a corkscrew. And all you're doing is increasing the distance going forward, which makes the grade less. Same concept with our driveways. If a house is on a hill, you can't make the driveway go straight into the garage because it would be too steep. So you make it curve a little bit and you make it longer, which decreases the gradient. Now, in some cases, we can make the hills shorter. Remember, for gradient, you can either make the distance going forward longer, or you can make the height less. And here's a case where a fairly large highway that the interstate couldn't go up and over the top of this hill. It would have been too steep at the top. So what they did was they cut the hill in half and they made the height lower. Obviously, this is tough to do. You got to move a lot of rock and you got to cut a lot of stuff, very time consuming, but sometimes you have to do this. And this is why you see some roads in the mountains with a cut in the mountain. What they're doing is they're making the road go to a lower height, which makes the gradient low enough that it's safe to drive on. Here's a case where they couldn't even do that. This is why we build tunnels. You can't make the mountain shorter and you couldn't make the road windy enough, so you just cut straight through. Tunnels are usually built where you have no other option to change the grade. A profile. Thing is, with all these topographic maps, they are all pictured like you were looking down from space. The trouble is, we're not up in the sky looking down. We look at things from ground level, from the side. So this is how we see things. We see things in terms of their profile, the view of the land as we see it from the side. Now, we can tell a lot about the gradient from this. We can look at it and see where it's steep and where it's not steep. These are helpful because this is how we see stuff. Here's an example of an elevation profile. Say this is a path that you were walking. You can see from 0 to about 4 miles, and you can see some places it's pretty steep and some places it's not. Here's a typical elevation profile of a trail in Yosemite National Park. And you can see there about 5 kilometers, it doesn't seem to be going up in elevation. It seems to be pretty flat. Well, let's look at 5 kilometers in. You can see, yeah, it's not going up very much. This is a pretty flat part of the land, and we can tell that by looking at it from the side. We can look at its elevation profile. Now let's look up here at kilometer number 11. If you notice at the end, it seems to go up really, really quick in a short period of time. So it'll be a pretty steep grade. Let's take a look at kilometer number 11. That's what kilometer number 11 looks like at the end of this trail. You can see you're going up really, really quick. The land is very, very steep. It's so steep, as a matter of fact, that you have to have a cable to hold on to walk up it. This is question number 16 that I need you to add to the bottom of your notes page, and that's, what can an elevation profile quickly tell you about land? A profile tells you not how much the elevation changes so much, but how it is changing. It can tell you where the land is steep or not too steep just by a quick glance. You don't have to do any math. You don't have to look at the contour lines. You can just kind of look at this and see, oh, on one side it's steep and on the other it's not. So that's where profiles are useful. They tell us how the land is changing, how steep it is, what the grade might be, without having to read a fancy map and to do any math. When you have finished your notes, and especially after you've added this question number 16, bring it to me or Miss Daly, and we will give you a done stamp for the day. Secure them in your notebook for use at a later time.